Hello everyone. So in this video we are going to learn today the experimental setup that was used to study the photoelectric effect and the observations that were made during this experiment. So here you can see a basic circuit diagram in which we have two metal plates, okay, one on this side, and here for the simulation I have taken this metal plate on the left of sodium. Okay, so as you can see here at the bottom right corner, the metal we are using is sodium Na, and the work function for sodium is around 2.27 electron volt. Okay, I hope you remember what was work function. It is the minimum energy that we must supply to a metal so that the free electrons in it comes out of the metal surface. They are emitted from it, right? And that is what we call this phenomena of emission of electrons using light is what we call photoelectric emission or the photoelectric effect. All right, so this is sodium, all right, sodium metal, and here we have a normal metal plate as the collector. So it will be just collecting the electrons that will be emitted by this sodium plate. This entire setup of the two plates are inside a glass container which has been totally made or converted into vacuum. So basically there is no air molecule present inside here. Okay, now this setup that we have here of the batteries and the resistor is used to change the potential difference across the two plates. As you are going to see with the simulation, I will show you how we can do that. Here this one here is a voltmeter which is right now at 0 volt, basically meaning that there is no potential difference across the two plates. And as a result, here you can see we have the ammeter which is also showing a value of 0, means there is no current flowing in the circuit. As you know from current electricity chapter that for a electric current to move through a circuit, the circuit must be closed, right? So that electrons can easily go from one point to another. But here you can see in between these two plates, there is no metallic part present. There is no conductor. So of course electrons cannot go from one side to another unless they get sufficiently high energy that they can jump from one point to another. Okay, so here electrons cannot simply move from one plate to another because no conductor is in between. They have to make a jump, and to make this jump they need very high values of energy. The electrons have to come out of the metal surface, the sodium metal, and go to the other one. So let's see how that is going to be possible. Okay, so as I've told you that sodium is having a work function of 2.27 electron volt. Here on the bottom left corner, if you see, here we can adjust the radiation, the light which is falling on the sodium metal. All right, and right now our setting is at 549 nanometer wavelength. Okay, it is almost a green color. As you can see, this light is falling. Okay, frequency is around 546 terahertz, and the energy of this light is around 2.26 electron volt. So clearly you can see that energy of this radiation is smaller than the work function of the metal, right? As a result, you can see doesn't matter even if we increase the applied voltage. So you can see the voltmeter reading is increasing, and at the same time this rheostat is coming down. I hope you have noticed this arrow comes down when we are increasing the voltage. Now you can see it, I hope, right? This arrow here where my cursor is right now, it comes down. So I have taken here to a value of 5 volt maximum that is allowed. So you can see here this green dot was going towards the right hand side, means the voltmeter value is increasing, but the emitter value doesn't increase. It is still at 0, means there is no current. Why? As discussed, to have an electric current we must have a flow of electrons, but electrons cannot flow easily from this plate to the other plate because it is vacuum in between, hence no current. So the only possible way that we will see a current is if the electrons make a jump, for which we must give them energy that is at least equal to the work function. So let us increase the energy of the incident radiation. So here I am adjusting the value, and as you can see now I have kept it at 2.27 electron volt. Okay, so now the frequency here is 550 terahertz, wavelength is 545 nanometer. Okay, energy is 2.27 electron volt. Actually it is a little more than 2.27 in the higher decimal places. So you can see now these blue particles, which I think you can guess are the electrons, are getting emitted from the metal surface and they are going to the other plate, here the collector plate. Okay, then you can see there is a current of 1 ampere flowing, right? So we have a current of 1 ampere when the potential difference across the two plates is 5 volt and the energy supplied by the radiation is a little more than 2.27 electron volt. Okay, of course you see if it is exactly 2.27 electron volt equal to the work function, the electrons will just come out of the metal surface and be there. Very few of them will reach to the other side. Okay, so they need some kinetic energy to go to the other side on or inside the glass chamber. Okay, now let's see, if we decrease the applied voltage, what will happen? So here in the voltmeter, now gradually I'll be decreasing the voltage. Okay, let's see what happens. So as you can see, pay attention to the graph. The graph is coming backwards. It is neither going up nor coming down. It is moving to the left hand side here. Okay, then finally at a point you can see it is now starting to come downward when the voltage is around 2 volt, right? And finally what happens here, it becomes zero. So as you can see, when the potential difference is 0 volt, there is no potential difference, current has also become zero. It is because, as I said, we are applying energy almost equal to the work function. So the electrons do not have any extra energy to move from one point to another. Their kinetic energy is almost zero. That's why without any potential difference, they cannot move from one point to another. Okay, so the current has become zero, and if we keep on decreasing the voltage, means now we are making this collector plate negative with respect to the emitter plate. Okay, the emitter is now at high potential as compared to the collector. So you can see this graph keep on going backward. So simply there is no change in the current because there is no electron reaching the collector plate. As you can see now, there is no blue particles. Okay, so that we have seen in this one. Now let's do one thing. Here you can see the irradiation intensity, which is basically the intensity of light falling on it. Let me double this value. I am taking the intensity now 4. Okay, let's see how the current is going to change in this case. So as you can see, the voltmeter value is increasing. Initially there is no current. Why? Again, it is because you see there is a negative value here, right? Negative value means the collector plate is at a lower potential as compared to the emitter plate. So if this collector plate is negative, then it will repel the negative electrons which wants to go there, right? Electrons coming out of the emitter are negatively charged. If the collector plate is also negative, negative will repel each other, hence the electron cannot reach the collector plate. Okay, so that's why you see for these negative voltages we are not seeing any rise in current. But now can you see the moment potential difference becomes zero, now this plate is no longer negative, so electrons are able to come out, right? But still they don't have sufficient energy to go to the other side. They are just moving near the emitter plate. But if we apply a positive potential difference now, means the emitter is at a higher potential, so the positive emitter plate will attract the negatively charged electrons. As a result, the electrons you can see are moving to this side, giving a very tiny current. If we keep on increasing the potential difference, what will happen? The voltage will become stronger and stronger. More and more electrons will be getting attracted to the collector plate. So as you can see here, the graph is rising upward. Okay, and again you see after some time the graph becomes a straight line, means the current value is constant at around 2 ampere. It doesn't increase after that. Okay, let's see, let's make the intensity 6 times. Okay, now the intensity, so can you see the current has also increased now. When intensity is 6, now the current has become 3 ampere, right? Now if we change the voltmeter value, what you see again, of course, as the potential difference is decreasing, the current at first remains constant, then again it starts to decrease, and ultimately it again joins the graph here at the same point. Means when the voltage here became zero, current also became zero, and then doesn't matter how much negative you make it, you will not see any electrons reaching there. Okay, so these are the graphs that we see when we are changing the intensity. Keep in mind, we are keeping the frequency of the radiation constant. Throughout this video till now, I have not changed. After making the work function equal to 2.27, I have not changed the frequency here, right? So the frequency of incident radiation is constant. We only increase the intensity of the radiation. Okay, so what we found here, as we increase the intensity, okay, what we found that the maximum current that we get keeps on increasing. Like first, in this case, the maximum current was 1 ampere. Then we made the intensity 4 times. Intensity was equal to 4. Then we get a maximum current of 2 ampere. Now when the intensity is at 6, maximum current is at 3 ampere. Okay, so this was the experimental result that scientists got when they did experiment on this photoelectric emission. Now let's see for a higher energy value what happens. Okay, Suppose, let me clear this graph. Let's take the sodium only. Let me bring it to 0. Okay. So let us take now an energy of around, say, let's take 2.8 electron volt. Okay. So we are taking an energy of here, wait, 2.8 electron volt. Okay. Let me clear the graph. All right. Now you see in this case, we are having an energy of 2.8 electron volt in the incident radiation. The electrons need only 2.27 electron volt. Okay. So here we have an excess of around 0.53 electron volt, right? You are supplying 2.8 electron volt, out of which 2.27 will be used to come out of the metal. So now the electron has an extra 0. It will be 53 electron volt, right? So using this extra 0.53 electron volt as its kinetic energy, now the electrons can jump from the emitter to the collector even if there is no potential difference, or as I can say, even if this plate, the collector, is not at a higher potential. Let's see in this graph. So as you can see, as I'm increasing here the voltmeter values are increasing, as you can see. Now you see the voltmeter's value is at minus 0.1 volt, right? Means this collector is still negative, but we are seeing a rise in current. Okay, so this emitter plate, sorry, this black one is the collector plate. The collector plate is negative. It is trying to repel the electrons, but still the electrons are managing to reach the collector plate. How? Because now the electrons have some extra kinetic energy, 0.53 electron volt, right? So using this extra energy, the electrons are able to overcome the repulsion of the collector plate, and as a result they can reach the collector plate easily. So that's why we can see a rising current in this case. Okay, so it is rising, as you can see, as we're increasing the voltage, the current increases, and again it acquires a saturation value. Maximum is at 3 ampere. Okay. All right. Now, again, let's say take the value of intensity at 4 units. Okay. Then in that case, you see, again, if we change the voltmeter values, right now I'm explaining why we are seeing this. Okay. I'm just showing you what scientists observed, because that's how also they discovered. They first saw what are the results. They didn't understand why it is happening, and later only it was discovered why these graphs looks like this. Okay. So why part will be going later. First, we are just discussing what was observed. So again, if we change the voltmeter reading, you can see a graph which is again touching the horizontal axis at the same point. If we take the intensity to 2 units, change the voltmeter readings, again you can see a similar pattern that we saw earlier, right? For the green color light. So you can see the color here of the light is also changing, isn't it? Earlier it was green, now it is blue, and each, as I said, each of these small wave denotes one photon which are falling here. Okay. Now I don't know if you have noticed one thing or not. Say if I increase the intensity, say it is now 2, and you can see, say after some time, one wave is falling here, one photon is falling. If I double it, can you see these photons are now coming more rapidly? There are a lot of them are coming together now. If we make it 6 times, you see now even a greater number of photons are coming together, right? So this tells us that here in case of light, intensity tells us how many photons are falling on this metal surface. Intensity of light in this scenario tells us the number of photons which are coming and falling on this metal surface. Okay, that is the thing that we get here. So we now here have a similar graph as with the green light, but one difference, if you can notice, is that for the green color light, the current becomes 0 when the voltage was 0, but for the blue color light, the current becomes 0 when the voltage is at a certain negative value, around 0. Minus 0.5. Wait, let me see. So yeah, it becomes 0 at minus 0.5 volt, right? So even if the collector plate is negative, still say at minus 0.3, the collector plate is negative still now, right now, isn't it? But still the electrons are able to reach the collector plate because of the extra kinetic energy that they are having, and hence we are getting a current of 0.2 ampere. Okay, now you see at this value, earlier the current became 0 in for the green color light when the voltage was 0, right? Now the current is becoming 0 when the voltage is minus 0.5 volt. If I take a ray of higher radiation, higher energy, okay, say 3.28 electron volt, and if I change the voltmeter reading, okay, so here you can see the current became zero when the voltage is minus 1 volt. Okay, so you can see this voltage at which the current is becoming zero changes with the frequency of incident radiation. As we change the frequency, the energy of incident radiation is changing, and that's why we find that the potential here, which is required to make the photoelectric current zero, also changes. Now this potential or this voltage at which the photoelectric current becomes zero, even when radiation is still falling. See, radiation is still incident on the metal surface. Electrons are coming out, but they are not able to reach the collector. Okay, so this voltage at which we have the photoelectric current becoming zero for any given metal is what we call the stopping potential. Okay, the stopping potential or the cutoff voltage, because at this voltage or the cutoff voltage or the stopping potential, the current in the emitter becomes zero. There is no photoelectric current that we see. Okay, so this is what we call the stopping potential in this case. And one thing is clear, I hope you realize that as we change the energy of incident radiation, means we change the frequency of incident radiation, the stopping potential also changed, right? For green light, it was at 0. For blue light, it was at around 0.5 volt, minus 0.5. Now for this, it is basically ultraviolet light. It is not black, okay? It is ultraviolet. The color is, the frequency is more than violet color. So here we are getting minus 1. Okay, so this tells us as we increase the energy, as we increase the frequency of incident radiation, the stopping potential also increases, right? Simply because now you can guess, larger the incident energy, more will be the kinetic energy, right? Because see, it only needs 2.27. So the more you supply the energy, doesn't matter, even if you are applying say 3.28 electron volt, only 2.27 will be utilized by the electrons to come out of the metal. Rest, whatever energy is left, that will be converted to the electron's kinetic energy. Okay, so the higher the kinetic energy of the electron, the faster it is moving, and hence it is more difficult for this negative plate to stop the electrons. Okay, so from this we observe that first of all, as when the frequency of incident radiation is smaller than a certain value, then we don't see any photoelectric emission happening. Like when it was, the corresponding energy was less than 2.27 electron volt, there was no emission, right? So this minimum value of frequency is what we call the threshold frequency. Okay, so for incident radiation, there should be a minimum frequency depending on what is the metal, and this minimum frequency is what we call the threshold frequency, below which we can never see photoelectric emission. Doesn't matter whatever is the voltmeter reading, whatever is the intensity of radiation. Okay, secondly, we saw that as we increase the frequency of incident radiation, we were changing the energy of incident radiation, and then we found that the stopping potential kept on increasing, because the more the energy of incident radiation, higher will be the kinetic energy of the electrons, and as a result, it will be more difficult for the collector plate when it is negative to stop the electrons. Okay, so it is like that we see here. Now, and in all these cases, we found one thing, that as we increase or decrease the intensity of radiation, what we found that after a certain value, the current always becomes constant. You can see in this case it is 2 ampere, here it is 3 ampere. So this constant current, the maximum current, is what we call the saturation current, beyond which it doesn't increase. Okay, now why it is happening here in this case? Because you see, the incident photons will emit a certain amount of electrons, right? Now imagine in 1 second, the incident light is emitting say 10 electrons. Okay, 10 electrons are emitted per second. So if your potential difference is not very high, what will happen? Out of the 10 electrons, say 6 or 7 of them may go sideways. It is not necessary that all the electrons are emitted straight towards the collector. Some may go sideways, right? So for a low potential, okay, for a low positive potential, this positivity of the collector plate is not high enough that it can attract all the electrons. Say out of the 10 electrons emitted, only 3 are going towards the collector plate, rest 7 are going outwards from the side. Now as we keep on increasing the voltage, what happens? The collector plate becomes more and more positive, right? It has more higher potential, as a result of which it is able to attract more and more electrons towards itself. So now out of the 10 electrons, suppose say 8 of them are falling to the collector plate and only 2 of them are going out. Okay. Now finally, when the collector plate's potential is so high enough that all the 10 electrons that are emitted per second are getting attracted to the collector plate. Okay, so that's why you see after that, doesn't matter whatever be the highest value of the voltmeters reading, say up to 5 volt, you see there is no change in current. Why? What is current? Charge flowing per unit time. Okay, charge per second. So maximum we are getting 10 electrons per second, right? So even if you are making it more positive, it cannot attract any more extra electrons. Are you getting the point? If the emitter is emitting 10 electrons per second, the collector will receive maximum 10 electrons per second only. Okay, your supplier is providing 10 electrons per second, you will only get 10, never more than that. Okay, so that is why even increasing the potential of the collector plate doesn't necessarily increases the current here after a certain point. And as you can see, it is same for all of them, right? So this tells us that at a certain value of potential of the collector plate, we find that maximum number of electrons that are emitted per second are reaching the collector plate, and as a result here we find that the current acquires saturation. It reaches a maximum value. Okay, and one important thing I hope you notice, that this saturation current depends on the intensity of incident radiation. Okay, so as you can see here, for an intensity of 2 units, the saturation current is 1 ampere. When we double it to 4, the saturation current also double to 2. When we increase it to 6 units, the saturation current also increase to 3 ampere. So, and as I have told you, here you see increasing the intensity, what is happening? The number of photons falling here is increasing, right? So that is why the more the number of photons that are falling on the metal surface, the more will be the number of electrons that are emitted. As I told you in the class, that each electron will absorb one photon. Okay, so one photon can emit only one electron. So if you have 10 photons falling on a metal surface with sufficient energy, 10 electrons will be emitted, nothing more, nothing less. Okay, so if you increase the number of photons falling on the metal surface, means you increase the intensity, you will have more electrons ejected per second. As a result, you will have a larger value of the saturation current. Okay, so this increase in saturation current with an increase in intensity can be explained by the fact that when we consider light to be made of particles, photons, increasing the intensity means that we are increasing the number of photons which are falling on the metal per second, and as a result more electrons are emitted, so we get a larger saturation current. Okay, so this was about this graph in which we have a variation of saturation current with a variation in intensity. Okay, and for these three graphs I have again kept the frequency constant. I have not changed it. Okay, so now let's see in the next case we'll be doing is we'll be now keeping the intensity constant and changing the frequency of incident radiation. Okay, so I'll be now say intensity, let's keep it fixed at 5 units. Okay, now we'll be studying different graphs for different values of frequency of incident radiation. Let me take this to a negative value. Okay, and here now this is the stopping potential where the current is becoming 0. um, and I have, if you have seen, I have also attached a PDF file. We will find all these observations, experimental results, and the important definitions that you need to know. Okay, so these are all there, and later also I will share you some other important points of these experimental observations. Okay, now let's do one thing. Now I'll be not be messing up with the intensity value. It will be fixed at 5. Okay, so now you can see that let me take a round value, say okay 3.2 electron volt. The frequency is 775 terahertz. Okay, now let's vary the potential difference between the two plates. Okay, so here you can see I am changing the voltmeter reading, and you get a graph which is going upwards, acquiring saturation and so on, as we discussed later. So here, discussed earlier, -1 is the stopping potential, because below -1 you don't see any current is 0. Only after that you see the current rising. Okay, so this is what we get here. So stopping potential, I want you to note down that for this, just you can write in a rough copy, that for a 775 terahertz frequency, the stopping potential is around how much we are getting? -1.2 volt. Now let's change the frequency of incident radiation. Let's say take it to 650 terahertz. Okay, so for a frequency of 650 terahertz, now we are in the blue color region. You can see the color of the light has also changed to blue. The energy carried is 2.69 electron volt. Okay, again I'm not going to mess up with the intensity. Now let's change the voltmeter reading. Means we are changing the potential difference. Okay, so here you see this graph is again having the same value of saturation current. Can you see? The saturation current is exactly the same. Why? Because in both cases the intensity is same, right? Intensity is same means number of photons falling per second is the same. As a result, the number of electrons emitted per second is constant in both the cases. So we see the same value of saturation current. If for this ultraviolet black color light we had 10 electrons emitted per second, for the blue light also we are having 10 electrons emitted per second maximum. Okay, so that's why we have the same saturation current. But one thing if you have noticed here, that in this case the stopping potential is a different value, right? Let me take it back again. Watch the emitter reading here. Okay, so it is 0.76543210. So now you see the stopping potential is at minus 0.4 volt. Earlier it was around minus 1.2 volt, I think, right? So here it is now at minus 0.4 volt. So now with a smaller value of stopping potential 0.4, we are able to make the photoelectric current zero. Why? Because won't you agree that now the electrons will be going slowly towards the collector plate? Why? Think. It is because that now the energy of the incident radiation is less. So out of this 2.69, 2.27 will be already utilized for the electron to come out of the metal. Okay. So now the electron has only 0. It will be 4.2 electron volt of energy. A very less value, right? And that's why the electrons are now moving with a smaller kinetic energy. So a smaller negative potential is sufficient to stop them. So now only a potential of 0.4 volt of the collector plate, which is negative, is able to stop it. So we see the stopping potential changing here, right? Okay, if we take light of a even smaller frequency, say how much lower can we go? Oh, excuse me for that. Okay, so it is at 570 terahertz. Okay, so here you can see at 570 terahertz we had green color. Now the energy is 2.36 electron volt. Okay, so now you see I have changed this one, I think. Okay, 570 terahertz. If we change the voltmeter reading, so here you can see that as we are okay, I have again messed up, I think. No, that's fine. So as we change the voltmeter reading, you see now the graph is again showing the same kind of orientation, right? We are having the again same saturation current because we have not changed the intensity. But again here you can see there is a change in the stopping potential, right? So now the stopping potential is around minus 0.1 volt. Okay, so now uh, the energy of the incident radiation is 2.36 electron volt, out of which 2.27 will be utilized by the electrons to come out of the metal. So the energy left with it, the electrons is around 0.09 electron volt, very little, right? So for this 0.09 electron volt of kinetic energy, here what we find that the stopping potential is also very less, minus 0.1 volt only, which will be able to stop this electron. So you can see now there are no electrons here, right? Because we are having zero current, right? So this voltage is able to stop the slowly moving electrons in this case. All right. So this graph shows us that as we change the frequency of incident radiation, okay, what happens? The stopping potential also changes, right? And as we discussed, changing the frequency of incident radiation changes the energy of the radiation, right? And larger is the energy of the incident radiation, basically the energy of the photons, as we are talking about, we have large value of kinetic energy of the emitted photoelectrons. Okay, and if the kinetic energy of the emitted photoelectrons is large, we will also need a very large stopping potential to make the photoelectric current zero. And that's why you saw that for green color the energy where it is 2.36 electron volt, we have a very small stopping potential, minus 0.1, because of course the kinetic energy is very less for the electrons. For the blue color, they were having more kinetic energy because the energy of the blue color was larger, so we had a bit larger stopping potential there, right? And for this ultraviolet ray denoted by the black color, we had an even much higher stopping potential. It was around minus 1.2 electron volt, I think, right? So this shows us that the energy of incident radiation changes with the frequency. Okay, as we discussed in the class earlier, scientists thought that energy depends on the amplitude, or it depends on the intensity. Okay, but what photoelectric effect experiment showed them, that in case of light, which was considered to be wave, and yes, it was correct, in case of wave, the energy of the wave depends on the intensity or on the amplitude of the wave. But here we find that light, even it behaves as a wave, here the energy does not depend on the amplitude or the intensity, it depends on the frequency of incident radiation. Okay, and hence to explain these observations, the particle nature of light was proposed. Okay, and the main proponent was Albert Einstein, who showed us how using some simple equations we can calculate what will be the maximum kinetic energy of the emitted photoelectrons and how we can relate it with the stopping potential. Okay, so about this we'll be discussing in the next class. So I hope in this, through this experiment, you have got the idea about it, about these two graphs. So remember, in the first graph we kept the frequency constant, we changed the intensity of incident radiation. As a result, changing the intensity changed the saturation current, which showed us, since the saturation current was changing with intensity, means the number of electrons emitted changes with intensity. Okay, then now we saw that if we are keeping the intensity constant, the saturation current does not change, but if we are changing the frequency, we find that the stopping potential is changing. And it was clear to even scientists at that time, at the 19th century, that stopping potential will depend on the kinetic energy of the electrons. Okay, and as changing the frequency changed the stopping potential, this gave scientists a hint that changing stopping potential means the kinetic energy of the electrons is changing. And from where the electrons are getting the kinetic energy? From the incident radiation, right? Means that changing the frequency changes the energy of the incident radiation, and as a result the electrons are getting different kinetic energies when they are emitted from the metal surface. Okay, so this was in rough the experimental understanding of the photoelectric effect. All right, so what next we'll discuss about the Einstein's photoelectric equation, with which how we can measure the stopping potential, the threshold frequency, the work function. All right, and after this, as we saw that light exhibits dual nature, so wave nature is necessary, without which we cannot explain the five phenomena, namely reflection, refraction, polarization, diffraction and interference. And also using wave theory, since we cannot explain the photoelectric effect, here we need the particle nature of light. Means the light is not falling as a wave, but as you can see here, there are small tiny waves, tiny packets of energy, which we call photons, which are basically particles. Okay, so we need the particle theory of light to explain the photoelectric effect, and we also need the wave theory of light to explain the other previously discussed phenomena, the five phenomena that we have. Okay, so that's why light exhibits dual nature. It can also behave as a wave, as well as it can also behave as a particle. So later we'll see toward the end of the chapter that as radiation, means light, can exhibit dual nature, similarly it was found that material particles like electron, protons, or any other object you take, any macroscopic material object, can also exhibit dual nature. Means a material particle can also behave as a wave. Okay, so this will be discussing in our next class. I hope you got the idea from this. If you have any doubts or queries, note down the points, we'll discuss in the class. Okay, and through you can also go to the simulation yourself, change the values and try to understand the things, and you can refer to the NCERT textbook also. It is given nicely there, all the important things you will find it there. Okay, so see you in the next class. Thank you.